So let's look at some more examples of identifying the correct mechanism for substitution and elimination. Looking at our first example, all four mechanisms are possible because we have a secondary alkyl halide. Now what we're adding is NH3. There's no charge present, so this is most likely going to be weak, and it could be both a nucleophile and a base. Now for this, whenever we see something in the, like this, where something can be both a nucleophile and a base, and we are doing an SN1 or an E1 sort of process, if you add heat, the E1 would tend to be favored. If you don't add heat, usually it's the SN1 favored. Now, so this one, there's no heat being added, so it's SN1, because we have a secondary alkyl halide and we have a weak nucleophile. Because we have that weak nucleophile, the leaving group will leave before the nucleophile adds. The leaving group is better at doing its job than the nucleophile is. And so what we generate is a carbocation that looks like this. That is a secondary carbocation. Over here, we have a hydrogen that could shift to give us a tertiary carbocation. So that's actually going to happen. And then our nitrogen will add, and we will get a nitrogen, NH3 right here. That's going to be positively charged. Now nitrogen is NH3, ammonia is a base, and it can eventually remove the extra hydrogen to make our compound neutral. So this is the product of the reaction. We don't actually put our nucleophile on this initial alpha carbon because of the rearrangement, the hydride shift, to give us the more stable carbocation. We'll put our nitrogen right here instead, coming off of that carbon. So this would be the product of that reaction. Now on the right, notice we're adding heat this time. We have a tertiary alkyl halide, so we can only do SN1, E1, or E2. SN2 is out of the question. Because we're using ammonia, which isn't charged, that is a weak base, a weak nucleophile, we're going to do SN1 or E1. Now, because we're adding heat, that's going to favor the E1. So we first generate our carbocation by losing the leaving group. Remember, when you form a carbocation, you're going to an sp2 hybridization, so any RS sort of stereochemistry dash wedge chemistry is gone. So this would be our initial carbocation, and then we will do the elimination towards the more substituted Zaitsev product. Also, what's favoring this process is the fact that we are forming a conjugated, let me put those back, we're forming a conjugated alkene, and that's more stable than a non-conjugated. So we have these alternating double bonds that are conjugated. Next, we have a secondary alkyl halide, but we are adding this reagent here that is a strong nucleophile. Because of the sodium here, that's a spectator ion with a positive charge, our sulfur is going to have a negative charge, making it a strong nucleophile. And so it's going to do the SN2 process, kicking out the bromine. No carbocation forms, so no rearrangement will occur. And our sulfur is going to add, and it's still attached to the CH3. On the right side of that, we have a tertiary alkyl halide. So we're going to form our carbocation because we can't do SN2, and also because our reagent is a weak nucleophile base, there's no charge, we know it's not going to be E2, so a carbocation is going to be formed, SN1 or E1. Now, because we're not heating this up, we're going to expect the SN1 to be favored. Our oxygen would add with our CH3 still attached, and technically there's still a hydrogen there. That's going to give a positive charge on the oxygen. Well, through proton transfer, we're going to lose that hydrogen, and our product's going to be this. oxygen methyl group here is going to replace the iodine, specifically the oxygen's replacing the iodine, and is going to be bonded to the what was the alpha carbon in that one. No rearrangement occurs because we form a tertiary carbocation, which is stable, more stable than any possibility there. The one at the bottom now, secondary alkyl halide, all possible, but we have a negative charge here, meaning strong nucleophile or base potential. Because it is very bulky, it's going to be a strong base only, and we're going to do an E2 elimination. Now we have two beta positions. I'm going to call this beta 1 and this one beta 2. Both of these have hydrogens, so we could eliminate either direction. If we had a smaller base, we would favor the Zaitsev product, which is the more substituted. However, we have a bulky base, so we're going to remove the hydrogen that's easiest to get to, which is on the less substituted side. We're going to form our double bond to form the less substituted alkene, and this would be our product. Now, if we use something like sodium methoxide, or sodium ethoxide, or even possibly sodium hydroxide, those small bases would favor the elimination in the Zaitsev product, the more substituted thermodynamic product, which would have been that. Now, last, we have a secondary alkyl halide. We're adding water, which is a weak nucleophile, weak base, but because we're heating it up, it's going to favor the elimination. So it's going to act more like a base, and we're going to do the E1 mechanism. So we first form our carbocation. I didn't interfere with this carbon here, so it's still going to be a wedge for the moment. But that's a secondary carbocation. What can happen is I can shift a hydrogen over, do a hydride shift, to form a new, more stable tertiary carbocation. And then last, we do the elimination. Because we are heating this up in a weak base, we don't have to worry about bulky base being Hofmann. Usually when you do E1, we favor the Zaitsev more substituted, which would be either that, these are the same structure because of the symmetry there. Doesn't matter which one you drew, it's the same thing, don't draw them both, but that would be the product. We would not get the Hofmann product, which would be this, because it's the less stable product. So there's some examples where we did different mechanisms by identifying the alkyl halide as primary, secondary, tertiary, moving on to the reagent, whether it's a base nucleophile, strong, weak, bulky or not, and whether we heated up the reagents or not.